Mike Dudley here. We're going to continue in chapter 3. We're going to be talking about the control strip portion of your density testing. Learning objectives is again to continue to understand VTM 76, and primarily the focus in this presentation is to talk about how we construct a control strip and interpret the test results. This is the overview. You've already seen this a couple times. You'll probably see it again. But as you can tell from this layout, we've already done the roller pattern. We determined how many number of passes were required to get optimum density. Now we're moving into the control strip portion, which is where we verify that the density we did achieve meets the minimum requirement specification. After that, the next presentation will touch on test sections and how to interpret payment. So let's start with the construction process of the control strip. To do this, we want to establish, we use the nuclear gauge to establish an average reading of a control strip. This is done by testing 10 random locations. And basically, to verify the 10 density readings we get from the nuclear gauge, we'll be taking cores and measuring the actual density of those cores and compare it to what the nuclear density gauge gave us. When do we have to construct a control strip? VDOT specification requires one control strip be constructed at the beginning of work on each roadway and shoulder course and on each lift for each course. So basically, anytime anything changes on the roadway, we're doing a new control strip. Typically our sub base is different on the shoulder than it is on the main line. So there's a reason you see a different control strip required on shoulder than is on the roadway. When do we need additional control strips and when is this required? Basically, if anything changes from our source of material, maybe we change our JMF, our job mix formula. Maybe we were running a mix with 30% wrap and for some reason our wrap collar, wrap feed messed up, so we switched to a virgin mix for the remainder of the day. And that's a JMF change, so that's obviously a mix change. We would have to do a new control strip, verify our density at that time. If we've done a roller pattern control strip and our control strip fails, we have to do a second one. At this point, when we do a second control strip, if that fails, we must stop paving altogether. We have laid a certain amount of mix, a certain amount of roadway out here that has failing densities on it. We do not want to continue to lay a failing product. So we are required by specification to stop paving if we have 2 consecutive failing control strips and investigate why. Once we determine what the reason is, we can continue paving, but we must stop until that determination has been made. Here's just a diagram, an overview of the control strip. We already addressed the roller pattern previously. So we started from our paving joint. We laid between 500 and 1,000 feet. That's our determination. Once we've done that, we've done our 75-foot roller pattern. We rolled that to achieve optimum density. So once we got that break and we determined our optimum density, we had this area, this little buffer area of about 50 feet where we allowed the rollers to go back and forth to turn around. Now we actually start in the control strip. The control strip will be 300 foot long and is full pavement width. And we're going to construct this in the same manner as what we've done with the roller pattern. In other words, the roller pattern determined optimum density, whatever number of passes, how many vibratory passes, how many static passes that took with the same rollers, the same paver. Maybe this paver had the vibratory screed on, that must stay on. All that stays the same, and we'll construct this 300-foot control strip with the same equipment as we did with the roller pattern. And this is where we'll actually measure exact densities to compare this to see whether or not we're passing and meeting specification. But how do we pick the test locations? Where do we choose this? We know we got to take 10 readings, 10 test locations. How do we pick them? Do we flip a coin? No, heads or tails ain't going to give us a good location. Do we just guess numbers? No, we really can't just do roll the dice and guess numbers. What we want to do is what's called a stratified random selection. All right, because in a true randomization of a process, we got a 300-foot section of pavement here we're going to test. We could randomly be guessing 10 numbers or 10 locations in this 300 foot, and we could have all 10 of them be in the first 100 feet and the last 200 feet not even be represented. So in order for us to do what's called a stratification or stratified random choice of our testing locations, we're going to break this 300-foot section up into equal sections. For this example, we're breaking it in half with two 150-foot test sections. So from that, we had 10 readings that we were going to take total. If we're breaking it in half, we're cutting this down to 150 feet. We want the first 5 readings to come out of the first 150 feet and the second 5 readings come out of the second 150 feet, so that the total 10 readings is encompassing the complete 300 foot of pavement that is the actual control strip. The process we choose to use for this randomization anything we choose to do, we can get it approved by VDOT as long as it's approved by the engineer, and we are allowed to establish our own process. Here's just a table. This is typically what's given to you. A lot of times VDOT inspectors will have these with them. They give them to you on a daily basis, whether you're doing a control strip, a test section, or whatever. This determines where they want the test ran that day. So this is just an example you can find on page 314 in your book. Let's move forward into constructing the control strip. First thing you want to do when you construct a control strip is to mark where these test locations are, based on that randomization table we showed previously. When it's time to mark these test locations, we don't want to put the gauge on a mat and mark around the circumference of it. We want to have a template. It's actually required by specification to have this template. We'll show you a picture of it here in a minute. And you're to mark this template out, all 10 locations, before you start actually taking your readings. When we're going to run the test, the nuclear test, we're going to run it in the 1-minute mode. If you remember when we did the roller pattern, we ran that in 30-second mode because we were focused on getting it done quickly, and we were just looking for a breaking point or an optimum density point. And here we're verifying that optimum point meets a minimum specification. So we want to be as accurate as possible. In order to have that accuracy, we set the nuclear gauge in a 1-minute mode rather than 30-second mode for the control strip. Once we've taken all 10 readings, we're going to average them. And then once we've got our average, we're going to transfer those nuclear gauge readings, which we recorded on a TL58 form, to a TL60 form. You'll see those forms coming up here in a minute in this presentation. Based on that, we will at that point select the 3 sites that are closest to the average of the 10 readings we have taken. And those sites are going to be, cores or plugs are going to be taken at those sites. And that's the ones we're actually going to measure our density on through a process of bulking and determining the density of these sections of these cores. Do want to note here, if this is a subsequent control strip, what do I mean by subsequent control strip is we've already ran this mix with this equipment on a previous roadway. All we've changed is roadway, so now maybe our subbase has changed. We would still have to do it at that point because our subbase may have changed. We got to verify our control strip. To do that at this time, we're allowed to only take 1 core versus 3, which is just an interest of saving some time, because we're just verifying what we did previously still works on this new pavement, this new roadway. To continue with the process, once I've taken these cores, every test site that I choose to take a plug or a core at, I'm taking a pair of cores, not just one. You'll see this in some future pictures that I have that'll illustrate this. And we also have a nice core template that we're going to lay down on the ground that marks this so that the cores or plugs are the same size. We don't want them one place taking a 6-inch plug and the other place taking a 4. We have a standard size that we take, which is a 4x4 square, and we have a template we use to mark that. Then when it comes time to actually cutting these cores or plugs, whether it be a surface mix, an intermediate mix, or an SMA, we're going to dry cut these. We'll also show you how that's done. But when it comes to base mix, because typically that's placed at a thicker lift, we are allowed to wet core. That will take the time to dry out to verify that our densities are passing, but we are allowed to do wet cores for base mix. Here's the diagram, the template I was talking about. As you can see, the template in the upper picture here, and the technician is marking his location. The second picture to the right shows how it's marked, but also note that it's numbered. All 10 locations must be numbered. It doesn't have to be numbered right in the middle of the square, it can be adjacent to it, but it is important that all these 10 locations have a proper numbering for reference. Continue with the control strip. Just like what we said with the roller pattern, we don't want any density test to be taken next to the edge of the pavement. For surface and intermediate mixes, nothing within 1 foot of the outside edge, but for base mixes, no test within 1.5 feet of the edge. So if we have a test reading based on our random numbers for a base mix that says it should be taken at 1 foot offset, we would just move that over to 2 feet. If that actually happens and you had to adjust based on your random numbering that you had generated, you would need to note that on your test form, and you'd also want the inspector to note that change and the reason why. As said previously, when we're taking these readings, we're going to take these density readings or nuclear readings in the 1-minute mode. But one thing different than with the roller pattern, when we talked about the roller pattern, we said no readings would be taken in any overlap. Overlap is where the one roller pass is adjacent to the one right beside it, and anytime that happens, you have a 6-inch minimum overlap from the roller drums. So if you do have a random number that happens to fall in this overlap for your control strip, you do take the reading at that location. We don't exclude it like we did in the roller pattern. So it is possible to have some test sites have that be in that 6-inch overlap area if that's where your random numbers happen to fall. Once we've tested all the locations, we'll determine our average. Once we've got our average of the 10 sites, we are going to take our plugs, whether it be typically what is taken is 2 plugs per site. Cores are the difference in a plug and a core. A plug is the square cut specimen. A core is drilled out of the pavement and it's round. That's the difference in the two. But we are going to, for the for this control strip, we're going to be testing the sites that are closest to the average. Here's just an example of a form TL58. It's a little small here on the screen, but I wanted you to just see an overall example. We're now going to focus on more of the center portion of it. Here the center portion is blowed up, easier for you to see. And note, one of the first things you want to do, you'll have forms just like this when you do your exam or when you're in the field, and you would get these numbers from a random number table. For the exam, you'll be given the random number table. When you're working in the field, somebody will have handed you these random numbers, whether it be the inspector or whoever on the job site that will give you your test locations. So here we have, it shows where you actually transfer these numbers to the actual TL58 form. Now, the next thing we want to do, we would take our 10 readings. We record our 10 readings at those specified site locations, and then we're going to total them up and average them. Once we've averaged them, in this case you can see the average is 141.4, we need to go back and find which test locations are the closest to that average. In this case, the first site, 141.1 will be 1. Test site number 3 will also be a plug or core site, and test site number 5 are the sites that will be actually taking our plugs or our cores. To do this, we determined that sites 1, 3, and 5 were the closest to the control strip average. Do want to mention to you real quickly that if this was a subsequent control strip, which is you've already used this mix, this equipment, you just changed the roadway you're laying it on, the route you're paving, then you could get by with only 1 core. It wouldn't have us take 3 locations. But once we determine our average, it's important that we compare that average, and we just do this visually, with what we got from the roller pattern. For the roller pattern represented with this control strip, we had a density of 142.5. This control strip gave us a 141.4. It's important it basically just gives you a comfort that everything's going well, that you check this, that it be within 3 pounds of the roller pattern. And in this case it is. So we feel fairly confident that this control strip went well, everything's represented well, and we should receive passing density once we complete our testing. So once we've recorded all this data on our TL58, we're going to transfer it to a different form, which is TL60. We'll be showing that in a moment. And we're going to continue on testing our control strip. To do this, we're going to continue on with the next section here. We go to each location. We want to mark these plugs or cores. I'll show you some pictures of that here in a minute. And it's important when you're marking your plug or your core location that you make sure it's in the middle of the template area that you had marked out for your nuclear gauge to do its testing. Basically, you want to make sure the reading is between the source rod, which is in the front of the gauge, and the back of the thin lift nuclear gauge, which is where the density reading was actually taken, which is in the middle of the gauge area. We're going to, as I said already, if you're doing plugs, we're going to take 2 plugs or cores per location. We'll show you how that goes going forward. And if we're doing surface or intermediate mix, we're going to dry core. And if we're doing base, we will wet core, just because the pavement's too thick to get a dry core specimen. Here is a portion of the TL60 form. As you can see, note here that he's already transferred the data. It's on the far right-hand side from the TL58 to the TL60. That was his core. That was his nuclear density readings, and he's determined that we are going to core site 1, site 3, and site 5. We've also labeled those plug locations to be 1A, 1B, 3A, 3B, and 5A, 5B, which keeps us referencing to the exact same nuclear density reading that was taken at that location. Here, the technicians, there's a picture of the template for marking a plug location. You can see the picture on the left, he's marking it out with a marker. Picture on the right, he's already labeled 1A and 1B before he actually starts cutting. And if you look at this mix, you can probably recognize that we're actually doing this testing on an SMA mix. Before we do any testing, it's important that the mix is still warm, the mat's still hot. We want to cool it off. But in this little picture here, you see that the technician is actually using propane. Propane is not allowed to be used on the project due to safety. There are other products that will work. It can be dry ice. You're allowed to use dry ice. Most technicians, most people tend to use a CO2, carbon dioxide gas product to cool the mat. It seems to cool it quicker than anything else. Once the technician has cooled the mat, he's going to begin cutting it. He's basically going to cut on top of all the marks that he made previously. And you can see here how he's just basically cutting straight down. We'll actually prize the product out here in a minute. Once he's done his cutting, all the areas he had marked had been cut deep enough to get completely through the mat that was placed. He wants to recool the surface. The reason he does, that hot saw that you're using to cut these areas generates heat. So it's very important that we recool the area. In this case, the technician is using some CO2 to cool it off, and it also helps to clean off the specimen you're getting ready to remove from the pavement. Now you see the technician, he's beginning to remove these specimens. It's recommended that you use a rather wide spatula to do the prying. Basically, you stick it in a slot you cut and you just prise back and forth until it breaks free from the pavement below. I caution people using a screwdriver in this case, that the screwdriver is really narrow and it puts a focal point of pressure which can damage your specimen. And this is where you're going to measure your density, your actual density, so you don't want to damage it. It's important to have a wide spatula for this process, as you can see there in the first picture that he's using to help pry the specimen out. Here it is, a nice image of the specimen has been removed, and notice what's left behind is a hole. And by specification, we're required to both tack and fill these holes with mix. It's recommended that you use the same mix that you're laying the pavement with, paving the pavement with that day. Once we've removed our specimen, in order for us to measure the density or the voids or determine whether or not we pass and meet specification, we have to determine the bulk specific gravity of the specimen. This is done according to VTM 6. Here, the specimen, the first thing you do as part of VTM 6 is to weigh your plug or your core in air. And that's shown here in this diagram. You can see the specimen on top of the scale. The second step is to actually weigh your specimen in water. The specimen needs to be fully submerged in water for this to happen. None of the specimen can be sticking out. Actually, the only thing that should be breaking the surface of the water is a very fine wire type line. Some people use fishing line. Something small like you see in this image here is a good example of that. Your specimen has to be submerged in water for a minimum of 1 minute. And it needs to stay beyond that minimum of a minute until the mass or weight stabilizes. It sometimes can take a little longer than a minute, but you have to leave it at least for 1 full minute. That's to allow time for water to absorb inside of the specimen. Once we've recorded the weight in water, the next weight we'll need is what's called an SSD, saturated surface damp condition of the specimen, which is weighing it back on top of the scale. But in this case, you take the specimen out and with a damp towel, not a dry towel, a damp towel, you wipe off excess water, okay? Your specimen will still be damp, and then you just simply place it on a scale and record your weight. Once we've got those 3 weights, weight in air, weight in water, and SSD, saturated surface damp weight, we can calculate the bulk specific gravity for this specimen. And we would use the formula here. Do note that we always want to record our bulk specific gravity of individual specimens in a control strip to 2 decimal places. Here's just an example of a TL60 form. I know it's a big form on a small screen, but this gives you an idea of what the form looks like. Now we're going to focus on the center portion where we're doing most of the calculations. We're right back to where we were before. On the far right hand side is the nuclear densities that were recorded when we did our control strip. Our specimens are labeled 1, 3, and 5, A and B. First weight we'll take will be the weight in air. We want to record these weights in the air to the nearest 0.1 gram. The second weight we'll take will be the weight in water. Remember, when we're taking this weight in water, specimen has to be fully submerged. It has to be in the water for a minimum of 1 minute, and once that minute has passed, as soon as the scale stabilizes, we'll record that weight. Again, we're going to record that weight to the nearest 0.1 gram. Third weights we need is the SSD weight, or saturated surface damp weight. So we'll pull the specimens one at a time out of the water, dry them with a damp towel. Pardon me with saying dry them. We're just going to wipe them with a damp towel so that no water is dripping from them. place them on the scale and record that weight. Again, weight's recorded to 0.1 grams. After we've recorded all our weights, we're going to calculate the volume. That's the next column here on this table. Volume is basically the SSD weight minus the weight in water. So that's a simple calculation. You're going to record that here. Again, the number we're recording is to 0.1 grams. From there, we're going to actually calculate the individual bulk specific gravity for each specimen. Okay, we complete our calculation here. With this calculation, we want to report, as we said earlier, these bulk specific gravities to 2 decimal places. Now note that with specimen 1A and 1B, both of these specimens together represent the one nuclear density reading that was taken at site 1. So in order to continue on, we're going to average these 2 readings, and that is done so by adding the 2 together, dividing by 2. But when we report the average for this location, for sites 1A and 1B, we're going to report these specific gravities to 3 decimal places, as you see here on the form. So we'll do that for all 3 test sites, site 1, site 3, and site 5, and we'll end up with 3 bulk specific gravities that we've now recorded. In addition, at this time on our form, it's also asking us to measure the thickness of each one of the specimens. We just do that with a ruler, and you just write it down. You only have to record that to 1 decimal place as well. The next step, now that we've got our individual site location bulk specific gravities, which is the combination of A and B for each site, we're going to average those 3. All right, that's simply adding the 3 bulk specific gravities together and dividing by 3. Again, we're going to report this to 3 decimal places. We want to keep that going forward with specific gravities. Once we've determined the individual site location specific gravities, the bulk specific gravity for each location, we're going to average those out. We've done that by adding the 3 together and dividing by 3. That gives me a bulk specific gravity for this control strip of 2.253. Now I need to determine if that bulk specific gravity will meet the minimum density requirement going forward. To do that, we have to calculate the percent density for this control strip. I'll also need, for that calculation, I'll need to know the RICE. The RICE for this particular day's production, which in order for that to happen, you need to reach out to your lab and ask them for the daily RICE. The RICE for this day's production, or at this point through the day, is a 2.424. From that, I use the formula where I take my average bulk specific gravity, divide it by my RICE, times 100, and that's giving me a density of 93.0. The question is, does 93.0 meet the minimum specification requirements for this mix? To do that, we need to know what the minimum requirement is for this mix. The mix that we laid for this control strip was an SM 9.5D, and for this we're having to go to our table, which is table 3-3 of section 315. But note here on this slide on the screen, there's actually a supplemental specification out for this. So since there's a supplemental, we need to make sure if there's anything that's changed. What is changed is in supplemental specification 315-002020-04, section E, section 315.05 E, section 1A, paragraph 7 states, a lot of acronyms there. The control strip shall be considered a lot if the control strip density conforms to the requirements of 92.5% of theoretical maximum density for surface, intermediate, and base mix. The engineer will consider the control strip to be acceptable, and the control strip density shall become the target control strip density. So in this case, we had a 93 point, and this is the actual table. As you can see from that from that supplemental specification, and you can see for 100% payment and for everything to be acceptable, we needed to have a 92.5% minimum. In the case of our specimen, we'd write that on the form as a 92.5 minimum acceptable density, and we had a 93.0. So our control strip does pass and does meet specifications for this SM 9.5D. That means our target acceptance density will be a 141.4 for this equipment, for this mix, for this control strip going forward for any other test sections. Well, that's the target density we would be using going forward with this gauge of a 141.4. All right, let's do some practice. The study guide has a couple practice problems for you to work through. This will help you get some practice for what you're going to have to do on your exam, and then in your job when you're out on your pavement, out on your roadway doing your job. It's highly recommended that at this point you pause the video, work through the practice problem. Once you've completed the practice problem, start the video back up, and we'll step through the practice problems together. For Chapter 3, practice exercise number 1, this is a random number table you'll have supplied to you that gives you your test locations. This is the form TL58. It's going to be given to you on an example like this on the exam, or you'd be using a blank form without this data on it when you're actually working in the field. So back to Chapter 3, practice exercise number 1. Note here that the distance on the left side marked here for our control strip, this is our linear footage. And remember, we're doing a 300-foot control strip. So if we're doing a stratified random, the first 5 readings have to be within the first 150 feet. They are. They start at 23. On the 5th reading, it's 149. Then the next 5 readings will be in the second 150 feet, which goes from 176 to 275. So we're doing proper representation for this control strip. Also, the statement up top tells us that this is 11-foot wide pavement, and therefore you can see that you come over to the different distance from your reference line and to 11 feet, and this will be the offsets that we're using for each test location. First thing you do is transfer those locations to your TL58 form. That's actually important to do for your exam time. You may get an exam question that says, what was the test location on the control strip of test location number 7? And you need to, based on this data being transferred here, you would know it was a distance of 187 with an offset of 9 feet. You would be supplied these 10 nuclear density readings. You see them here already on your form. And as we've stated previously, the first thing you want to do is total them up and determine an average. So your average for this exercise is a 148.4. Looks like the 3 readings closest to the average are test site number 1, test site number 3, and test site number 6. So these are the locations we'll actually plan on taking cores. Here is an example of a TL60 form. This one's blank, this one is just like what you'll receive on the exam. And the first thing you want to do is, first off, transfer your data from your TL58 to your TL60. As you can see on the right side here, this is all our nuclear density readings been moved over, and we determined that Site 1, Site 3, and Site 6 are going to be our cores or our plugs. So we've labeled our specimens 1AB, 3AB, and 6AB. Next thing you want to do is do your calculations. Your weights would have been given to you. For our calculations, we'll calculate the volume for each specimen and determine the individual specimen bulk specific gravities, as you can see here. Once these values have been determined, the next step is to determine your average bulk specific gravity for each site. Remember, 2 plugs or 2 cores per site, A and B, will equate to 1 combined bulk specific gravity for that specific site. So we end up with 3 bulk specific gravities, which we're going to do as we did previously. We're going to average those 3 by adding them up, dividing by 3, and that gives us an average bulk specific gravity of 2.453. You can see down below that you have a RICE provided to you from the lab. It'll be given to you on the exam. That RICE was a 2.644. So from that, we can calculate a percent density for our test strip of a 92.8. Again, we got to verify if this specimen passes or fails the minimum density. We go back to the supplemental specification 315-002020-04, and that will tell us that the minimum density is a 92.5 for this particular mix, for surface mixes, and therefore our 92.8 for this control strip does meet the minimum density requirement of a 92.5 for this particular exercise. So our target density for this particular pavement going forward will be a 148.4, which is the average of our 10 locations. Next, it's recommended that you continue with practice problem number 2 in your study guide. And for this one, you can actually compare it to the answers in the back of your manual. They're back in the appendices, and you'll be able to see if what you're doing is working correctly. If you have any questions, please get with your proctor or moderator. Thank you.